Thank you for attending. Thank you for the invitation. I wish the weather was better, but it's very unusual. But it's cold weather. So I'm going to discuss today the work that we're doing in the lab. It's stochastic control, but I'll discuss a few more things, how to deal with certain issues that come up with small drones. First of all, everybody knows about drones. People try to use them either for commercial or military applications. But what people very often do not realize that not all drones are created equal. We have very large drones that are as large as a regular aircraft, right? And these are quite different than the smaller drones. And for example, these are move very slowly. They have a lot of capacity to put whatever you want in there. And if you try to do something with a smaller drones that you're most familiar with, that may or may not work. So what are some of the challenges that come with trying to build software for smaller, light, and very agile drones? I became familiar with this problem almost 20 years ago almost by accident. I had a student, at the time it was no PX4, and I asked my student to build an autopilot in the lab, just to learn how to do stuff like that. And he was very good. This is our autopilot we developed it was built around this rabbit, and it was running at 30 megahertz. It's kind of a joke right now, but at the time it was one of the most capable microprocessors. Nevertheless, we're able to build the whole thing. We did the camera filters, we did the communication, GPS receiver. He did an excellent job, and actually it's somewhere in my lab collecting dust. I don't know where it is right now. And we flight tested it, and he also created a ground station. What I'm trying to say here, and the moral of the story, is that when we started implementing wanted to implement some of the algorithms, my student came back and said, you know what, I cannot run these path planning algorithms because it doesn't fit even in the memory of this thing. So we start thinking a little bit about the limits that come with the computational resources. So very often what happens is that you develop an algorithm, especially in the academia, then you give it to someone else to implement it on board, on the hardware, and it may not be appropriate. So very often you need your algorithm to be consistent with the hardware that it is available, right? You're not going to buy necessarily a new computer for you just to run your algorithm. So we start thinking how we can scale algorithms, particularly in this case, graphs algorithms. And we're able to run sophisticated planning algorithms on board using a combination of wavelet decompositions and some splines that create virtual corridors and things like that. And we flight tested it. We had to use several tricks that we implemented this. This is a decomposition using multi-resolution hard wavelets inside the memory. This is how you visualize it. And we have to use tricks like doing that in integer arithmetic and in-place operations that it was very, very fast. You're actually shifting register at that point using integer architecture. But that was this is one of the challenges that computer hardware, although things have been improved since then. Still, I believe that you cannot do as many things as you would like to do, at least as you would be capable of doing if you had a larger aircraft. The second thing is that these drones operate in a very unpredictable or very often messy environment. There's a lot of uncertainty. And you have to have certain guarantees in performance. And you have to guarantee performance, although there are constraints into the problem. One of the problems that I worked on, and again, this is kind of on older work that I'm presenting here, is how to deal with small drones in wind fields. Again, one of the issues is that the wind for small aircraft like this one could be a big proportion of the whole velocity, right? A big aircraft, if it flies, I don't know, like a couple of hundred miles, it is the wind, the relative wind, it's not a big proportion of the speed. But if you have a small drone like this, then the wind will affect tremendously what the result of the trajectory is going to be. Here is from a paper that we wrote a couple of years ago, shows if you, this is the wind speed, and you can see if you change the wind, how the path is deformed based on the wind speed. okay, and the direction and the strength of the wind. And that tells you that if you have some idea about the wind field, that you can use it to your advantage. For example, if you want to go from point A to point B, you can use the wind field to intercept someone faster than someone else who didn't have that information. So we developed a lot of kind of game, pursuit evasion game type of algorithms to take advantage of the wind fields. But today we're going to discuss a little bit about how to, actually simple architecture to deal with aerodynamic effects, including winds, when you try to do planning for these types of small vehicles. Again, it goes without saying that flying in windy conditions produces a lot of complex aerodynamics. The important thing here is that there are sophisticated methods to take care of that. People have developed CFD codes and things like that to deal with aerodynamics, but we want to do that fast. Okay, so we need to get solutions that are good enough to be able to run on board. Okay, of this. So it's not the most sophisticated method, but it's something that works pretty well, and you can run it on the fly at the hertz that you're interested in. Okay, so let's keep that in mind. All right, so the key idea is very, very simple. All right, so it involves two steps. The main step is to try to characterize or figure out what the aerodynamic forces are acting on the vehicle, try to cancel them. You're not going to cancel them exactly. There's going to be some left over, so you try to do as much as you can. You have some adaptation module that works in addition to that. I'll explain very quickly. There is a very simple Kalman filter to figure out what the wind conditions are. And then on top of that, you'll be left with a leftover. And I'll show you that if you do your job correctly, what the leftover is going to be basically noise. Okay, and then I'll show you a work, that's a more theoretical part of the work that show you today, how to deal with this noisy system, okay, using some new techniques that have been developed in the last 5 or 6 years about stochastic systems. So, okay, so here is the key idea. I'm only assuming a position control because I have, let's say that maybe at px4 that takes care of how the forces will be distributed. So I will, don't worry about attitude. I mean, I'm assuming there is a low-level control that takes care of everything. I'm just going to focus on position control, okay? And basically, here's the aerodynamic force. You probably not know that. You don't know that, but here is the usual equations that torque here, and I'm assuming that I can substitute this with some control, and I'm controlling this, and I have a low-level autopilot that, controller that will take care of how distributed to the actuators. Okay, so well, I'm going to take the control force, and I can try to cancel everything I can. So U is going to be my new acceleration, okay, command. And then I'm going to cancel gravity, and I'm going to try to cancel the disturbance here, which is the estimate. That's a hat here, is the estimate of aerodynamic force. Now, of course, you cannot cancel it exactly. We're trying to do as best as you can. So this is the estimated aerodynamic force. Then you have a new control, and if you write down the equation, it's very simple. Basically, you get something which is very simple to use. People know that for some time now. You basically get a double integrator. Of course, people these days, you can use either inner loops, flatness, differential flatness, and things like that. But at a high level, it looks like a double integrator. Very simple thing to control, except the fact that you have this extra term here that is the error that you committed trying to cancel the aerodynamic force. So how are you going to do that? First of all, this is a very complicated phenomenon. If you want to try to do it exactly, there are many influences coming from the body. There is influences coming from a rotor drag and all that stuff. I will focus only on the big influence, the body. People have shown that that's the main thing, at least for these things that I worry about. And basically, what am I going to do? I'm going to use a combination of model-based techniques, some idea about what I think the force is going to be, and then some machine learning on top of it, a neural network to take care of the things that I don't know about. So essentially, this is how it looks. So this is an estimation. Again, this is by no means a unique, but essentially it involves two parts. One part has a constant multiplied by the relative velocity. W is the wind velocity, V is the velocity of the vehicle, plus some extra term here that depends on Q. Q is the quaternion that tells you the attitude, and this is eta bar is the rotor speed. And then multiply by the relative velocity. Turns out that this is actually not a bad model for the regimes that we're interested in. The good thing is that the W, which the wind that you don't know, appears linearly, and that's the reason we use this this model. And this allows us to develop a very simple Kalman filter that will estimate you do an adaptation, right? So you're running this and you adapt to the wind based on a very simple model using a Kalman filter. So this is equations if you care about. So basically it's a standard Kalman filter and you have estimator and you update. This is the propagation of the covariance, the gain filter, and then the update for the wind estimation. Here is an example that shows how this thing works. So performed rather, the blue is some measurements, and here is the orange is our estimate for what the drag force is going to be. This is a competing algorithm, also one of the state of the art, which is based on incremental nonlinear inversion model. You see they're using a low pass filter. But you can see it's much more noisy. But using the Kalman filter, we can get a very good clean estimation. But okay, well, we do that. Still, this is not exact, but we did our best. And then we plot this after we did the experiment. Say, okay, we try to cancel best. What is the error? And the error turns out to look like this, and it's pretty Gaussian. So I said, okay, so far so good. Based on this preliminary cancellation of the things that I care about, I get a linear system subject to some noise, and this noise seems to have a Gaussian distribution. So how do I deal with that? Well, that's where going to the stochastic control part of this presentation, where I'm looking at this problem, and I'm going to go back to a more theoretical investigation. Since I'm primarily a theoretician, I basically have a linear system subject to Gaussian zero-mean noise. So this is the problem I have. And this is, I have a linear system, right? And this is the noise here. And the problem I'm going to solve, or I'm interested in, is a little bit different than what you're familiar with when you open a book. Okay, this is based on theory that's been developed for the last I guess 6 or 7 years. Okay, so I'm going to solve the following problem. I have some initial condition that is distributed according to some Gaussian distribution with some mean and some covariance, and I want the final position to be distributed according to some mean and some covariance. In addition to that, I have chance constraints. These are stochastic variables. So I want the probability that the state belongs to some safe set to be larger than some number, let's say 99%. And the probability that your control effort will be in the correct set to be also. All right, so this is a following problem to motivate. Let's say that, to explain a little bit why this is different than what you have been used to, let's say that I want to go from point A to point B and ask you how to solve this problem. This is, you can solve this problem. This is control theory 101, okay? Kalman told us how to solve this problem for linear system. There's actually a closed form solution for solving this problem going from point A to point B, okay? And this is one of the first things that graduate students learn when they take a multivariable control class. But I'm going to change the problem a little bit. And the problem is, suppose I give you a bunch of points, initial conditions, like some cloud of points, and I want to go to this cloud of points, and I want to move all of them at once. Okay, that's quite a different problem right there. Now, why I'm interested in this? This is what I mean here, that I want my final state to hit a particular, so I want from my initial distribution to a final distribution. So I'm not moving one point, I'm moving a cloud of points at the same time. Okay, why I'm interested in this type of problems is because, think about the things that we're interested in. If you have, let's say, this vehicle wants to land, okay, you may want to land, but there are some winds, right? And if you want to maintain, let's say, a field of view, you want to go down, but there are different realizations of the wind, and you want to guarantee no matter what the realization is, you're going to hit that target there. Okay, so you don't want to control one trajectory, you want to control a bunch of trajectory, and no matter what this cloud is going to be, it has to be inside this terminal set. So that's an example. Here's another example for a landing. All these examples are taken by aerospace application system and aerospace department. You want to land here, but their noise, of course, the vehicle may choose different paths depending on the unknown noise, but you want to guarantee no matter what, you're going to end up in this, let's say, cone. This is the constraint that you have. You can think of other examples, like you want to land, you want to draw some delivery, or you drop some package and you want to hit a particular spot with high probability, like an ellipse, a landing ellipse of some sort. Okay, by the way, this problem that I just mentioned is not clear that has a solution. Okay, so it's not clear that this problem here, that you can move a bunch of points from an initial point to a final point, is going to work. It's not clear that this is a solution. So the first time somebody answered this problem was Brockett, that basically said, yeah, this problem has a solution, and it is indeed controllable. So you can have it, but they do not offer a solution. Turns out, however, anyway, this is that basically is a problem of controlling distributions from an initial to some Gaussian distribution. And it turns out that this problem actually is easy to solve. It turns out to be a convex optimization problem. All right, so now we have all the ingredients, and we can go back to our problem. So this is the final architecture. Okay, so remember there are 3 steps. 2 steps rather, one offline step that I learn a neural network the gains to be able to plug it in here, and this neural network, along with the Kahneman filter, predicts the drag force. The drag force takes care of most of the bias, or the most of the deterministic part, I would say, of the model here. It is adapted according to the Kahneman filter, and then I have this extra controller here which is based on this theory I just described, this Kahneman, this covariance theory that actually allows you to take care of also the stochasticity. So here is a couple of examples to demonstrate, and I think I'm almost out of time. So this is an example. This is in the lab at Georgia Tech. We have a flight facility, indoor flight facility with a Vicon system, and we just did some standard stuff. Okay, so you're gonna do a figure 8, right? So but there's gonna be some initial distribution here. I'm not gonna start necessarily here. I'm gonna start in this circle in this case, anywhere in there. This is a 3 sigma ellipse of the initial distribution of this Gaussian distribution, and I want no matter what, you cannot see it very clearly, but there is another smaller circle right in the middle. I want to do figure 8, and I want to guarantee that as you do this figure 8, you're going to remain, no matter what, in this tube, virtual tube of trajectories, let's say, that guarantees that no matter what, you're going to be able to meet the specifications. And that's exactly what's going on here. Maybe have a video here. It's not, okay, just basically doing some figure 8, and this is the experimental data that you see that every green trajectory, it's one realization, one experiment, and you can see you start anywhere there, and actually the trajectory ends where it's supposed to go. And we have this is another example, similar example here. We have a virtual cone, and you want this to land. This is an example I showed you earlier, that maybe you want to land somewhere, and you may have some this cone, and you want to make sure that you're going to be able to move inside this cone, and no matter what, you need to guarantee that the specifications are met. And so that's all I had. Basically, a couple of takeaways. I think small UAVs need to account again for the aerodynamics. Otherwise, you're not going to get the performance you expect. We presented one solution here. This involves a hybrid model that has a deterministic part and some model-based part, and some part that takes care of uses a machine learning or a neural network. And if you do the job correctly, then you move all the biases, what you'll be left with is just stochastic noise, but you have to deal with the stochastic noise as well. And then you have another loop that takes care of the stochastic noise using stochastic, this new theory of stochastic optimal control based on controlling distributions of trajectories, not a single trajectory. Because of the way this theory works, on controlling distributions, it's not difficult to figure out that this actually works, and we have done it. It can be used for swarms of UAVs because you have like thousands of UAVs. It's better to see them as a swarm or as a particles in a distribution, so you can control the whole distribution much easier if you go to the limit and see it as a partial differential equation of some sort. So you can use the same ideas, and we have done it. So maybe I think that if you want to learn a little bit more, you can look at my website, and I'll be happy to answer any questions. Thank you very much.
Are there any questions?
And I'll be around for a few more hours.
Nice.
I'll be around.
All right, 1 second. 1 second. Let's do only like 2 questions because we gotta jump into something else, but please.
Thank you. Thank you, Ramon. Thank you for the presentation, Professor. The question is, would the calculation of this correction signal, would it improve if you have RTK information, like a higher resolution rather than GPS?
What's the main difference between the two?
The resolution. So with the regular GPS, you get meters.
The more you have, the better it is, right? I mean, if you have better measurements, you're going to get a better.
You get centimeter resolution with RTK.
Yeah. So we use we flew indoors, so we use a Vicon system that right. Mm-hmm. So it's kind of we had to use this fan to create a wind field to get a. Yeah.
And what would you recommend for a large system? Because we built a heavy lift octocopter and wind was an issue.
I guess you're asking what is the best way to. I think the performance is, in my opinion, it depends on how accurately you estimate the wind, right? Yeah. Now, there are a couple of different ways of doing it. Now, if you have a big aircraft, maybe you can put some sensors and things like that, right? If you don't, the way we did it here, and actually was, I didn't mention it carefully, but you can see the paper. So we use accelerometer measurements, and based on the accelerometer measurements, because you know what you command, so you know what the vehicle, if your model is good, you know what to respond. So you take this difference between what the vehicle did and what the vehicle did not do, and basically based on that, you figure out, what did not happen is because of external forces, mainly aerodynamic forces. And this is how to predict, because in the Kalman filter, as you can see, we have a measurement of the drag. I mean, we didn't have a sensor to measure the drag. We did it based on accelerometer measurements. So that's one way of doing it. If you have a sensor to measure, some people do that. They have a measure to, and again, you can do sophisticated things. You can run particle filters or something like that. But for a small UAV, small computers, it may not be possible. So that's why we went with a very simple linear Kalman filter to be able to do everything on the fly at the time scale that we wanted to. Yeah.
Thank you. Mm-hmm. There was one last question. Who else? Who was it?
I had one, but you already answered.
Okay, cool. You have one? Okay.
Thank you, Professor. What are some challenges when you try to extend this stochastic control to swarms?
First of all, there are not any big challenges in the sense that, theoretically speaking, the problem is exactly the same. One of the differences, one of the challenges that you may have is, first of all, the theory that we develop and is very clean. I didn't go to the details. You get a convex problem. It holds for the case that you start from a Gaussian distribution to a Gaussian distribution. Now, if you have a swarm, you went to the swarm to do, I don't know what the performance is going to be, right? I mean, you can start from any distribution. You want to go to any distribution. We have some results that you can. But what we did there is to extend these results, and I didn't cover that, from mixture of Gaussians to mixture of Gaussians. So mixture of Gaussians is really flexible enough to get these distributions. One issue that interesting is that what about collision avoidance? And that's one of the first things that comes to mind. But it turns out you get that for free, actually, if you do it properly. The reason is that because you model the swarm as a fluid, it turns out that fluid lines cannot intersect. So just by the physics. So you get that, I mean, if it's a particle, right? You have to make it a little bit larger. So in reality, they may collide. But in theory, you get that for free. So I don't see any direct showstoppers. Actually, we have planned it, and I didn't present it, but if you read this, we can discuss. We have actually done a lot of work on using this type of ideas for swarm control. You have basically start from a mixture of Gaussians, you go to a mixture of Gaussians. Actually, you can see the things they split. Some of them go, there is an obstacle, some of them go from one side of the obstacle, some other go to the other side of the obstacle, they go through the corridor or whatever. You can do. It's a natural thing to do if you have many swarms. The question is that at which point this approximation becomes, well, good enough. If you have 10 vehicles, is good enough to model it as a fluid that evolves? Probably not, but you have like 1,000 or 2,000, I would say, 1,000 swarms moving information identical. You get this so-called mean field theory that you can actually model it as a particles in the fluid that they move along particular lines. Yeah, there's a lot of work actually in this area. I'm not the only one who's doing that, but we have some good results. But yeah, any other questions?
All right. Thank you so much, Doctor. That's it.